get to the memory of Gregor Nicolis. So what I'm going to show you is just a simple experimental work. Our goal was to create a relatively simple device to study reaction diffusion patterns and phenomena in open chemical systems. A device which is easy to make, flexible, and provides a lot of options for the experimentalist. Um, when pattern formation discussed, especially in context of biological patterns, the two main ideas which are often cited or applied is the reaction diffusion theory introduced by Turing, which is based on the interaction of nonlinear kinetics and diffusion, especially differential diffusion, and the Wolpert's theory on interpretation of such a kind of gradient in the system. Um, I would like to note that in most of the cases when we perform experiments in open system to study reaction diffusion patterns in chemical system, we do have gradients as well. So the two things are often combined. So let me remind you to the two most often used reactor configuration and this field. When we do some experiments with chemical or sometimes biochemical systems, we like to apply these two configurations. In one case, it is called two-side fed reactor, and the other one is a one-side fed reactor. The two-side fed reactor operates in a way that it has two chambers with the complementary chemicals. So let's say chemical A in one chamber, chemical B in the other, and they diffuse into the middle inside the porous materials, which is often a hydrogel, and they react somewhere in the middle. So definitely we have a strong cross gradient in this kind of reactors. And the other, which is also often used, is the one-side fan configuration when we have a continuous tank reactor, which also in connection with the connected to a porous material and gel, and then the chemicals diffuse into the gel from the CSTR and may react again in the middle in the depths of the gel. So here we have also some gradients often. So, and it will be interesting at the second part of the talk, the presence of gradients, I think. So our idea was that to create something which looks quite similar to the two-side fed configuration, but now to create channels in a hydrogel. So we have at least two separated channels, which is in red and blue in this, and then we flow the chemicals into these two channels, and they diffuse into the gel, and then may react and then produce some patterns. Um, Originally, in our mind, this was that we can create really a quite similar situation to a TSFR, but it is not like that. I will discuss this part later on. So let's start with some experiment. I told you at the beginning that we wanted to create something which is simple, useful, and flexible. So this is just this crude picture shows you the cost, how to create this gels with channels. So basically, you need some holder and just tubes, and you fix your tubes at the beginning. You pour your gel. Once the gel is fixed, then you just pull out the tubes, and you have the hollow gels with channels, and you can vary easily the distance between the channels and the channel diameter and other geometrical parameters what you want. So it's really easy to create this sort of reactors. At first, we decided to test our device if it can operate in a way that we want, so we can reproduce some previous experimental observations. So we applied known chemical reactions which are known to produce some interesting patterns and tested in this new device. So this is just a picture of a precipitating reaction. Then we have calcium and carbonate, and if you flow the calcium and carbonate in two channels which are separated, then you get a relatively sharp precipitation zone in the middle. But you can have a sharp zone also by applying a homogeneous reaction. This is an acid autocatalytic reaction. We flow the chemicals of the components of this reaction, and then we observe the formation of an acidic stripe, which is yellow in the picture in the middle. So that's quite simple. So let's do something more dynamical, more interesting chemical reactions. So if we perform an experiment with an reaction which is ready to produce temporal oscillations. For example, like using a pH oscillator, which is a kind of extension of the previous acid autocatalytic process. Then what we observe is just um, then we flow the chemicals in the channel, and in the middle zone we get nice spatial temporal oscillations or waves, if you want to call them. So that operates nicely. We also tested our reaction, this one, in the chloride iodide malonic acid reaction, which is a very famous reaction in this field and known to produce a lot of interesting phenomena. So if we inflow the chemicals of the reagents of this CMO reaction, then we could also observe the formation of waves, which looks quite similar, but have been observed many years ago in standard two-side fed reaction. And even this configuration is ready to create, I mean, one can observe easily stationary pattern formation during like patterns. This was this raw spot appeared in between the two channels. So the question is it really just as a convenient TSFR or something else? And to answer this, let's see what is the concentration profiles in a standard TSFR when we have one side where we have, for example, one reagent at some concentration. So this is the source of our reagent B, and the other side is just a sink of B, and we have a linear concentration profile, so fixed gradient. But once we once we replace this standard configuration with this two-channel configuration, we have something else, because here we get a bipolar diffusion field. So this is just a diffusion field without any reaction. And now it has definitely there is no it has an inhomogeneous concentration and gradient fields as well. So while the first one, the standard TSFR, is just basically determined geometrically by the distance between the source and the sinks. Here the distance between the source and the sinks is important, but also it's become quite important the distance from the borders. So because definitely a two-dimensional bipolar diffusion field, and now we study the pattern formation in this field. So if this is just a simple simulation, if you just perform a very simple reaction, A plus B produces C, D, and E as a final product, then you can see in this bipolar situation the concentration profiles of a simple linear reaction is also separates. Okay, what is more interesting to perform some kind of nonlinear system, and this is a model of the pH oscillators what we applied successfully in the experiments. So it produces a sharp change in the increase in the hydrogen concentration, and then a decrease depending on the amount of component C. And the stationary profile in this bipolar medium, it's not, it follows the concentration fields, and we have an extended acidic zone on the sides because the extension of the reaction is higher and thinner in the middle. Now, if we check the oscillations in numerical simulation in this bipolar situation, then what we see that the acidic region appears from the sides. That's not surprising, and then extend in the direction of the middle zone. It may not enter there, so it depends on the concentration. But in some cases, if you change the parameters, then the two acidic zone even merge in the beginning, and then it returns. So this is the oscillations from the side view. And so this shows immediately that this bipolar situation is not exactly the same like in a standard TSFR. I want to point one simple aspect. If we just change the position a little bit of the channels, so now the distance from the border on the top and on the bottom is not exactly the same, just a very tiny difference exists between the two, then we get oscillations. Then we have some asynchronous oscillations on the two sides. That can be interesting to study even experimentally. So why our system is interesting and what we expect as a further directions. First, we believe that this simple device can be successfully applied to perform non-equilibrium synthesis. I mean, it's an interesting idea to perform synthetic chemistry at non-equilibrium conditions when we, for example, keep stationary concentration gradients. And we, just to test it, we created some metal organic frameworks, zinc imidazole frameworks, and also gold nanoparticles in this kind of non-equilibrium system. That would be also interesting to study, to create a flow through channels in a chemoresponsive gels, when now we can build really a chemical system by flowing the reagents through these channels, and then we would see the motion of the gel from outside. This is actually just a dream, but we have started to work on that. But if we can create 2 channels, we can create much more. That would be also interesting. For example, if we create 3 channels, then we can create 2 oscillatory special temperature oscillating zones on the 2 sides, and that would be interesting to study their interaction. We have performed some experiments also and some simulations in that direction. And finally, if we can create 3, we can create even more, at least in simulations, but I think it would be also easy to do it experimentally. So we can create a multipolar diffusion fields, like quadrupolar or hexapolar fields, and then we can study reaction diffusion patterns in this multipolar diffusion fields. So with this, I almost use my time, so I'm ready and open for any questions. Thank you for your attention.
Thank you very much, Itsvan. So, very nice system, very promising. So, are there any questions? So please raise your hand or just switch on your camera. And whereas I don't see any question for the moment, I was wondering, is the geometry of the section of your 2 tubes, let's say, whether it's a square or a circle, does it matter in terms of interaction between the zones?
At the moment, I don't think so that it's crucial. Of course, I mean, close to the channels, it has an effect on the diffusion, on the concentration field, definitely. But since the patterns appears not really at the neighborhood of the channels, I don't think that it has a very serious effects. But it can be interesting to study to create different geometries for the channels. Of course, in experimentally, the easiest is just a circular channel, but they can create other things. But I don't know at the moment.
Okay. So any other question? Yes, Juan Perez Mercader. Juan, can you maybe switch on your camera?
Yep. Good morning, everybody. Thank you so much for a very nice talk. And I have a couple of questions. One of them is, how long is the typical period? I missed it in the transparencies. You were so fast. And the second question is, do you understand the production of radicals during this oscillatory period, oscillatory events?
I mean, we apply different chemical systems, so the period of this chemical system is basically determined by the chemical kinetics. These are well known. So in the pH oscillators, this is on the time scale of several minutes, like 10 minutes or even longer. In a similar reaction, it's quite shorter. It's just a few minutes, but it depends on the chemistry what you apply in this kind of device. So radicals. That would be interesting, because I think this type of reactor configuration may allows us to also to study, I mean, to understand more the role of some intermediates, because as I showed you, that the intermediate separates in space. So I can imagine that someone can develop a method to study the composition of, I mean, to make a 2D plan of the composition of the gels, and then you can study what happens with the intermediates. Radicals, that would be difficult, but even radicals can be somehow detected.
Yeah, thank you. Thank you, Anne.
Thank you. Thank you. So thank you, Itsvan. Maybe you can
Yes.
your